So here we'll take a look at a problem from the 2007 BC exam. This was for response question number 6. It was a non-calculator question. And really all they gave us in the setup here is that we have a function f defined like this, e to the negative x squared. And what it asks us to do in part A is it asks us to write the first 4 non-zero terms and then also the general term for the Taylor series for f about x equals 0. And since it's a Taylor series based at 0, it's technically also a Maclaurin series. So the best way to go about this would not be to use the definition of a Maclaurin series to manually try to produce that series. What you want to do is you want to use a known Maclaurin series. This series right here converges to e to the x for all real numbers. And so if we start with this series, and I'm calling this function e to the x h of x here, and you'll kind of see why in a minute or two. But we have a series that converges to h of x, e to the x. In expanded form, it'd be written like this. So here would be the first 4 non-zero pieces, and then also the general term. Well, f of x is related to h of x. You can actually express f of x as h of negative x squared. Right? The only difference between f, which is up here, and h, which we've defined on this line, is that we have negative x squared going in place of this x. So we can re-represent f as h of negative x squared. And what's really easy to do is to then take the rule for this series and replace the x within it with that same term, with that negative x squared. So we're replacing the x that you see sitting here with negative x squared. In expanded form, those first 4 non-zero terms and then also the general term, what's that going to end up looking like? Well, it's going to end up looking like what I have here. So I just took this line here, which converges to h of x, and I replaced all of the x's with negative x squareds, and that will give me a series that converges to h of negative x squared. I then simplified it a little bit, so that's what you see on this bottom line here, and that would answer part A. In part B, we're going to use our result for part A, so we're going to use this bottom line here for a limit that we're going to try to evaluate in part B. So in part B, they want us to try to evaluate this limit. So it's kind of a goofy limit. If you just try to toss e to the negative x squared here and try to use L'Hopital's rule to evaluate this or try some different things, you're not going to have a lot of success. What's actually going to be nice is to use that answer from part A, as they suggest, to help us evaluate this limit. So we had this series at the bottom of the previous screen. It's in this set of parentheses right here, and this series converges to f of x. So rather than expressing the limit the exact same way it is here, or by simply putting this in place of f of x, I've put the series that converges to f of x in place of f of x. What I notice right away here is if I distribute this negative in, I have a 1 and I'm going to have a minus 1. And then if I distribute the negative into this term, I'm going to have a plus x squared. Well, I have a minus x squared here and a plus x squared here. So really these pieces are going to cancel, and these pieces are also going to cancel. That's just going to leave me with all of the stuff that sits here with this negative distributed into it. So you'll see negative x to the 4th over 2, and then the sign of this x to the 6th has changed, and then I just kind of am showing that the pattern is going to continue. One thing that you do notice that I've done, this general term right here, the power on the negative 1 has changed from just being a k on this top line to now being a k plus 1. And the reason why is because if we distribute a negative into this, that's going to give us one more factor of negative 1. So I've just kind of added 1 to this exponent, right? I'm multiplying by one more negative 1 when I distribute the negative into that general term. Well, this doesn't look very nice right now, but what you will notice is that now you have a common factor in your numerator. In your numerator, you can factor out an x to the 4th. And the benefit in doing that is you've got an x to the 4th sitting in this denominator, and you're going to be able to cancel those x to the 4ths. So when you factor x to the 4th out of the terms in your numerator, the first term is just going to be left with a negative 1/2. The second term, you're going to have an x squared still when you factor x to the 4th out of this. You're going to factor x to the 4th out of all these pieces. When you factor x to the 4th out of this piece, it doesn't really affect anything here, as we'll talk about in a minute. But when you factor x to the 4th out of this, you're technically dividing by x to the 4th. So when you divide x to the 2k by x to the 4th, you're dividing like bases, and when you divide like bases, you subtract your exponents. You're going to have the exponent from the numerator minus the exponent from the denominator. Once you have this product expressed here, you can cancel those x to the fourths. Now, check out what happens when you put 0 in place of all the x's. There's a 0 here. All these terms that we haven't shown are going to have a 0. This term is going to have an x that a 0 is going to go in place of. The only term we're left with is negative 1/2, and therefore that limit is going to equal negative 1/2. So here's a situation where using a series actually helps us evaluate a limit. In part C here, they want us to write out a new Taylor series. They want the first 4 non-zero terms of the Taylor series for this definite integral. Well, what we have is we have a Taylor series for this expression. So if we just put that Taylor series in place of e to the negative t squared. Now you will notice I changed the variable, right? The variable here is t. The variable in our series from part A was x. So I've just replaced the x's in the series from part A with t's. This would be 4 non-zero terms. And then I'm going to just use FTC part 1 here. So fundamental theorem part 1 says do the antiderivative of this now. So the antiderivative of 1 with respect to t is t, and then the antiderivative of the rest of the pieces will end up looking like this. So if you check out this piece, you add 1 to that power, you get 5, you divide by 5, you're going to have 5 times 2 in the denominator, and then similarly add 1 to that power, you get 7, and then divide by 7, you're going to end up with a 7 times 6 in that denominator, giving you a 42 there. Now put in the limits of integration, put in x. So when you put in x, you get these terms, and then subtract what you get when you put 0 in place of the t's. When you put 0 in place of all these t's, every term becomes a 0. So taking the difference is just going to leave you with the 4 pieces that you're left with by putting in that upper limit of integration. So here would be the first 4 terms in the Taylor series for this definite integral. What we then want to do is we want to estimate the value of the integral from 0 to 1/2 of that same expression, that same integrand, and we want to use our result here in order to help us do that. And we just want to use the first 2 terms, right? Use those first 2 terms in order to make that estimate. So the integral from 0 to 1/2, since this is going to approximate this integral, I would just have to put 1/2 in place of my x's in order to make my estimate. So when I put 1/2 in place of my x's, and then just do some arithmetic, I end up with 11/24. In the final piece of this question, they ask us to explain why that estimate from part C is going to be within 1/200th of the actual value of this definite integral. And so here you're kind of at a crossroads. You can try to use the Lagrange error bound, which is something you've discussed with regard to Taylor series. It's tough to pin down, it's difficult to work with. What we can kind of fall back on here, if we go back and we look at this, the beginning of this series, the first 4 terms of this series, this is an alternating series. This alternating series right here converges to this integral if we extend it infinitely. Well, the error involved in an estimate of a convergent alternating series by using the first few pieces is going to be within the value of the first term that you've left off. So you'll see what I've constructed here is I've constructed the absolute value of this term right here, x to the 5th over 10, but I've put 1/2 in place of x because our estimate at the end of part C required us to put 1/2 in place of the x's. So the first term that we left off of this estimate down here, if my computer will cooperate, there we go. The first term we've left off within this estimate would be plus 1/2 to the 5th over 10. So that means this estimate for the value of this definite integral is not going to be further off than the first piece we've left off, which is 1/2 to the 5th over 10. So in part C, what I've done here is I've kind of done a little bit of arithmetic with that 1/2 to the 5th over 10. You raise 1/2 to the 5th power, you get 1/32. We'll multiply by the reciprocal rather than dividing by 10. That gives you 1/320th. Well, 1/320th has a smaller numerical value than 1/200th does. So that's how we are 100% certain that our estimate in part C is going to be accurate to within this amount.